All right, let's get started. So we are continuing the theme of unfolding polyhedra, and the sort of general picture we were thinking about in terms of edge unfolding versus general unfolding, which are these two pictures. Top is an edge unfolding of the cube, bottom is general unfolding of the cube. If you have a convex polyhedron, we found general unfoldings. There are like 4 of them that work. We proved one of them. If you want an edge unfolding, that's the centuries-old open problem. For non-convex polyhedra, we know this is too much to hope for. Even if it's topologically convex, there's not always an edge unfolding. That was the tetrahedral witch's hat. But for general unfolding, we don't know. And so today's lecture is actually mostly about these 2 open problems and different variations of it that we know how to solve. Special cases and changes in the model. And at the end, there'll also be some stuff about the reverse direction folding. But mostly will be about unfolding. So there's a third kind of unfolding, which we call vertex unfolding. And it's kind of like a hinge dissection. So instead of normally an unfolding, something like cross, it's, a nice connected polygon. The faces are joined along edges. But what if I allowed disconnecting along edges, but I just wanted things to stay connected along vertices, like at a hinge? So it still should be one piece in the sense that this is still connected. And in fact, in this case, I still want an edge unfolding. I mean, you're only allowed to cut on edges. And in fact, we will cut on all the edges because that'll be the most flexible. Every edge gets cut, but you're going to leave intact certain vertices. To make one, quote, piece at vertices. So we still want one piece. So this is vertex unfolding, and it's always possible. We've even implemented this algorithm here, a bunch of random points on a sphere, take the convex hull, and then take a vertex unfolding. So you get this nice chain of triangles, don't intersect each other, and this will fold up into that 3D polyhedron on the left. Here's some bigger examples, hundreds of vertices, amazing. And all right, so how do we do this? All right, let me state a theorem. Every connected, triangulated manifold. This is a very general result. It actually holds in any dimension. We're going to think about 2-dimensional surfaces in 3D, but it could be d-dimensional surfaces in d+1 dimensions. Has a vertex unfolding. And so this works both for convex and for non-convex. The only catch is that every face has to be a triangle. It's an open problem for something like a cube where you actually have quadrilateral faces. So the way we prove this is to construct what we call a facet-path. This is a path that sort of alternates between visiting faces, triangles, and vertices. So the idea is you have some, let's say we're doing a tetrahedron or something. You start at a facet, then you go to one of its vertices, then you go to one of the facets that shares that vertex, then you go to one of the vertices, then you go to a facet, then you go to a vertex, then you go to a facet. This is a facet path. It should visit every facet, every triangle exactly once. Vertices you can visit multiple times, although I think it's a bad idea to visit the same vertex twice in a row. Other than that, you can visit a vertex more than once. Maybe I would visit it again coming up here. If there was another triangle like this, I could go up to this vertex again and over to the triangle. So the claim is facet paths always exist for any triangulated connected surface. Once you have this facet path, you're basically golden because you can lay it out without overlap. And that's next picture. So if you have a triangle and you have some corners of it that are hinged to adjacent triangles, you can rotate that triangle till it fits in a vertical slab. And the hinges are on the ends of the slab. And so each triangle lives in its own slab. Slabs don't intersect. No intersection. So that's once the hard part is really getting this path. Once you have that, you can just sort of lay it out. It's a little bit non-trivial with obtuse triangles. They don't necessarily just lie along a horizontal line. You have to set things up so that those guys are on the boundary. But you can always rotate it so that that's possible. So the real question is, how do we construct a facet path? All right, so I have a bunch of triangles. In general, they make some surface. And maybe I should draw a running example over here. Let's think about a triangulated cube, something simple. Imagine there's more triangles in the back. It's a little hard to think about the 3D picture. I would really like to two-dimensionalify it. And because this theorem works not only for polyhedra, it works for any manifold, any sort of locally two-dimensional thing. It would be nice if I could just sort of cut this open and think about a disk instead of a sphere, topologically. And I can. I mean, this theorem is supposed to work for disks just as well. It should work for anything that's connected. So ideally, I cut it all apart into lots of little triangles, but it has to stay connected. So I'll unfold it. Why not? So I can add some cuts until I get down to a spanning tree of the faces, spanning tree of the dual graph. Okay, for whatever reason, this is the unfolding, or this is the triangulation I chose, and this is the unfolding I chose. But I can just keep cutting edges until cutting an edge would cause it to disconnect. So the maximal set of cuts, because there are many ways to do it. When I unfold, it might overlap, because we don't know whether edge unfoldings exist, but that's fine. Just you can think of it as a two-dimensional picture, but it might need a few layers. We're not going to actually fold this thing, but we're going to cut this up into a facet path. This could actually be our input. Instead of being given a polyhedron, we're given a disk like this, triangulated disk, and we have to deal with it. Somehow we've got to construct a facet path here. Visit every triangle exactly once, and passing through vertices. Yeah, overlap doesn't really matter. We're going to cut it up, and then we're going to splay out the triangles. No, right. From the perspective of facet path, distances don't matter. It's just topology. Yeah, you could think of it as a circle with various some decomposition into triangles, if you like. But that's maybe harder to think about. I'm going to think about it this way. It's useful because then we'll get to Mickey Mouses, as we'll see. But, so, cut edges until you can't anymore. So until cutting would disconnect. So this means what you're left with will be a sort of a tree of faces. There'll be no cycles, because if there was a cycle, you could cut one of the edges and it wouldn't fall apart. So obviously there's a tree here. Now trees have leaves. That's our favorite lemma lately. They have at least 2 leaves. In the case of a triangulated polygon, we usually call them ears. So here's a fun term. So let's say color the ears. These are leaves in that tree, which we call the dual tree. So in reality, we're thinking about a dual graph, which looks something like this, where there's a vertex for every triangle and edges for every edge connecting triangles, and then there's leaves of that tree. But in the original thing, we think of this triangle as being an ear, and this triangle is an ear, and this triangle is an ear, and this triangle is an ear. I like ears because they're kind of on the boundary, on the surface. So they're just triangles that are adjacent to only one other triangle. Now, next step is to color what I would call sort of the second level ears. I'll call them the remaining ears. If you remove those ears, what would then become an ear? All right, now I wish I had another color. That's kind of yellowish. So this would become an ear, this would become an ear, this would become an ear, and this would become an ear. I'm going to stop there, just 2 levels. What could I get in this process? I mean, what it looks like I'm getting is I get an ear and then a second level ear. Could be a little more general than that. Maybe, for example, if I had a triangle like this, both of these would be first level ears, and then this would become a second level ear. Turns out that's all that can happen. Because these are triangles, second level ear, I mean, at this point, it's only adjacent to one other thing. So what was it adjacent to before? Well, maybe 1 ear. Certainly not 0 because it wasn't a first level ear. So at least 1 ear, maybe 2 ears. That's it.
Unless there's only 4 pieces left, right?
Sorry, what do you mean?
You have 3 ears.
You could have 3 ears. Yeah, so here I have 2. I mean, the first level ear and a second level. Or it could be a first level. Oh, you're saying at the end. Right, it could be like this. That will only happen at the very end. But yeah, this could be first level ears, and this is a second level ear. Good point. Most of the time, we will either get something like this. The rest of the polygons over here. So this is a first level ear. This is a second level ear. Or again. This is the Mickey Mouse picture. Probably not allowed to say Mickey Mouse. It's under copyright. But there you go. So 2 first level ears, second level ear, boom. This is most of the time what you'll get in the base cases of this induction. I'm going to pluck off these ears and keep making the thing smaller. At the end, there are a few cases to think about. I have them drawn here somewhere. Base cases. Nothing. Yeah, well. This won't work out if you have 1 triangle. If you have 0 triangles, which is this empty picture, or if you just have 2, maybe. Well, I guess, yeah, because then these are both first level ears. It doesn't look quite the same. Or maybe just a Mickey Mouse. Because those are all, well, that probably works. Anyway, these are the sort of cases you worry about. But for these cases, I just need to check that I can find a facet path. So for example, this one, I just visit the triangle. This one, I don't know, I do it like that. In fact, I can make it a cycle if I want to go crazy. This one, I don't know, something like this. That'd be one way to do it. Got to be a little careful. Still don't. Something like that. All right, but really I care about these 2 cases. So what I'm going to do for each of those, I guess this is still step 4. Is I actually want to make cycles for these guys. I care about that. Am I doing something wrong? Oh no, over there. Good. So in both of these cases, I can make cycles. In this one, in the base cases, not always, like this guy. Hard to make a cycle. But for the two general cases, if I find 2 years or 3 years, I can just draw that in. So I'll do that for this example, though by now it's gotten a little messy, so let me redraw it. So we have so I'm going to connect these guys and connect these guys. In this case, I only get the 2-year case, but I think we'll get another case shortly. Okay. So obviously I haven't finished it, and these are disconnected. There's lots of things left to do. But then the idea is repeat. So imagine those guys as being done. I'm left with these 4 triangles. And actually, a little boring, but because I don't get the Mickey Mouse case. But then this will be an ear. This will be a second level ear. And so I'll end up doing this. And this will be an ear. And this will be an ear. So second level ear. I mean, this is actually the base case, if you will. So in general, I just pluck off 2 or 3 triangles, repeat until I get one of the base cases. Now what I have is not connected, but it's a bunch of cycles. Right? There's one cycle here, one cycle there, one cycle there. You could actually connect some of them together like these two. You could go around like this and then go like that. So that could be a bigger cycle. But these cycles are not even attached to these cycles, so it's kind of a problem. That's step 5, is we're going to fix all the problems. It'd be a great title. Connect cycles together. We're going to do that by local switches. So here's a general picture. Suppose you have 2 adjacent triangles and 2 completely separate paths. So you know it's a cycle. So some cycle over here. And if this guy shared a vertex, then I could actually connect them together. So suppose it doesn't share a vertex, that means it has to use these 2. And then it something like that. What I want to do is remove this edge, and instead add this edge and that edge. So that's a local change, and now it will be one big cycle. We've probably seen this trick once or twice before. I think in the Mountain Valley assignment stuff. So here, I have, for example, these 2 triangles, which are adjacent, but the paths don't meet. So I'm just going to erase this edge, put in that one, erase this edge, put in that one. Lo and behold, I have a bigger cycle now, like that. Okay, still not everything. So like these 2 triangles don't touch. So erase that edge, put in that one, put in that one. I'm preserving at all times that I'm a facet path, and I'm merging components. So by the end, I'll have one big component. Now, I haven't necessarily described this as a big cycle, but as I've kind of been hinting, what I do now is take an Euler tour around this thing. You've seen Euler tours. All the vertices in this graph will have even degree, and so I can take an Euler tour. And really, I should take what's called a non-crossing Euler tour. Point is, you've got a bunch of cycles that touch. You just walk around the outside. That will visit all the cycles. It'll visit all these edges exactly once, and that will actually be a facet path. And we're done. Now I have a facet path for the triangulated cube. So I can splay out those triangles, get a non-overlapping chain like this. Actually, it's probably the top one. Something like that. Might be. I may not have matched exactly what's in the textbook. Cool. One slight detail is I was sort of waving my hands assuming there was actually a cycle here. I really only need a path In fact, there won't always be a cycle because at the very end, you're not able to construct a cycle. So that will actually cause you to make, if I do something like this, so at least it can connect to other things, that will cause you to make two vertices of odd degree. But that's okay. There's still an Euler path that starts at one of the vertices of odd degree, visits all the other edges, and then comes to the other vertex of odd degree. And I just need a path. You can actually characterize when you get a cycle. It's when the original thing is not too colorable, I think. Anyway, that's vertex unfolding. It's kind of easy. I think we solved most of it in like an afternoon. We had this idea, it was cool, and then we solved it kind of quickly. That's how it often goes. Once you have a cool problem, it falls quickly. There's lots of interesting open problems remaining about vertex unfolding, and they seem a lot harder. So, for example, what if I have non-triangulated polyhedra? And natural version is to think about, originally we were trying to attack convex polyhedra. This turned out to not require convexity, but what about convex polyhedra not triangulated? Is there always a vertex unfolding? We don't know about edge unfoldings. And the answer is no. Well, no, that's not right. Sorry. The answer is we don't know. What's annoying about this example is that there's no facet path. So there are two things that could go wrong. One is that the facet path doesn't exist, and that can happen in this more general scenario. And the other is that when you lay it out, it overlaps. Both of these things could go wrong in the general convex case. So in this example, it's a truncated cube. There's 8 triangles and only 6 octagons. And if you look, once you're at a triangle, you have to go to an octagon because there's no adjacent triangles. So at best, you could alternate triangle, octagon if you want to pack all those triangles in. But you run out of octagons to get there. So there's no facet path. But maybe you don't need a facet path. You could make a tree. Just a little trick here. Obviously, if you triangulate that surface, you're done. So the analog of general unfolding with vertex unfolding is trivial. You just triangulate, and then you use the edge case. But if you really only want to cut along edges, this example can be done. I mean, it has an edge unfolding. So if it has an edge unfolding, it definitely has a vertex unfolding. But we don't know how to prove it. The other thing that could go wrong is once you have octagons, even if you could sort of find a way to lay them out, that's not a very good octagon. You can't, let's say if your 2 hinges were here and here, if that's where you attach to adjacent pieces, you can't fit that in a vertical strip. There's no way to turn it so it fits in a vertical strip. So also this layout problem doesn't work if you have something more than triangles. So some pretty fascinating questions. It's even open for non-convex. If I take non-convex polyhedra and I want a vertex unfolding, let's say all the faces are convex. At the very least, you need to forbid faces having holes. If you remember this example. Box on a box. This also doesn't have a vertex unfolding because again, still this guy has to fit in that little square hole. But as long as the faces don't have holes, let's say the faces are convex, would be a nice version, like the spiked, like the witch's hat, the spiked tetrahedron. That probably has a vertex unfolding. If you triangulate this, it'll definitely have triangulate anything, it'll have a vertex unfolding. Yeah. All right, that's all I want to say about vertex unfolding. And that's sort of addressing edge unfolding of convex polyhedra, or actually both of these. Now I'd like to go to this sort of the real problem. This is one of my favorite problems. I think a bunch of us posed it in 98, which is right when I was, or 99, right when I was starting out. It's tantalizing, in some ways more natural, because it's nice to allow cuts anywhere. And it could potentially work for everything. I conjecture every non-convex polyhedron with that boundary can be generally unfolded. And there's some really good evidence for this as of a couple years ago. That's what I want to talk about. which is orthogonal polyhedra. This is one of my favorite unfolding results. It's by Marilla Demaine, Robin Flatland, and Joe O'Rourke. They've done a lot of work in this unfolding area. An orthogonal polyhedron is one where all the faces are perpendicular to one of the three coordinate axes. So for example, here is a orthogonal polyhedron I drew this morning. If you want to draw orthogonal polyhedra, Google SketchUp makes it really easy, and you can add shadows and texture. And all right. So there are three kinds of faces. There's the ones perpendicular to x, that's like these guys. There's the ones perpendicular to y, that's all the yellow faces. And there's the ones perpendicular to z, that's these top guys. So we call them x faces, y faces, z faces. What we're going to do, so the theorem is these have general unfoldings. That's pretty awesome. This is because, I mean, every polyhedron is approximately orthogonal if you can voxelize it. So this is really a lot of stuff. I would love to generalize this approach to arbitrary polyhedra, but that's the big open question. So what do we do? Well, we're going to single out, as from this color coding, the y faces. Just color them yellow. Then there's all the other faces. Well, they form bands. They're cycles. They go around in a loop. A lot of them here I've just drawn as rectangular loops. But in general, all those wooden faces, the x and z faces, will form a bunch of loops. And you can think of them, and then there's the y faces, which we're going to have to deal with, but sort of ignore them for a while. I should have drawn it with them erased to look cool. But if you think about just those bands, this is sort of how they're connected together, this tree. There's a big one out here, and then it has two children. There's this one and this one. And then this child has one child hanging off of it, and this one has two children hanging off of it. So that's these two guys. Okay, in general, this guy might have some children hanging off the backside as well. I'm not going to try to represent that in this picture. There's just a bunch of children. There'll be some front children and some back children. You pick some root arbitrarily, and then you have children going off of there. Now, if your orthogonal polyhedron has genus 0, it's topologically a sphere, this will be a tree. If it's like a donut, it will have a cycle. So this theorem only applies for genus 0. So we're going to exploit that dual drawing. I mean, how the bands are connected together is like a tree. So why don't I write down a band is a cycle of x and z faces, and they are connected together in a tree. Now the rough idea is we're going to take a depth-first traversal of this tree. We're going to start at the root, work our way down, come back up, work our way down, and something like that. It's not going to be quite so simple. The challenge, I guess you could say, is avoiding overlap. Okay, if you wanted to unfold a band, obviously a band can just unfold straight. It's like a nice long strip. So each band individually is fine. It's how do you paste those bands together and then have room for the yellow faces to attach on the sides. No overlap. But it can be done with the awesome, crazy idea, which we'll get to shortly. It's going to start out kind of innocent, but let's see. The general approach is always proceed rightward. In the unfolding. So it's going to look, the unfolding will look something like this. Okay, whatever. Always going to the right. We start here, and we might go up and down, but we never go left. And then that's going to be all the band faces. All the band stuff will be connected like that. And then there's going to be yellow faces that can just hang off the sides. So these are the Y faces. As long as I can get the band to do this, Y faces can hang up and down. It's not going to intersect anybody. Pretty clear? So it's clear if we could do this, we could get non-self-intersection. The amazing thing is that this is possible. What this is essentially a limitation on is how far you can turn sort of your bearing. So you start going right. You can turn right, but I could not turn right again. I have to turn left next. I can actually do 2 left turns in a row as long as I was initially going down. I can turn left twice, and I could alternate left-right. That's always good. Or I could turn right twice, but only if I'm initially going up. That's the rules. As long as I adhere to those rules, I'm fine. Now, we're going to heavily exploit that we can do general unfolding, that we can subdivide those strips into lots of little pieces. We're going to subdivide into a lot of little pieces, an exponential number of pieces. So this is kind of hardcore. So here is one example. This is a leaf. So trees have leaves, and at the end, we're going to have to visit a leaf. So this is one box. There's these funny views, so you can see like a mirror on the bottom and a mirror on the right and on the side. So this is sort of, if you had one box, here's what you would do. And we're actually assuming, notice this side does not get covered. The idea is that side doesn't exist, that's attached to the rest of the polyhedron. So that's where our parent lives. And our parent tells us, you have to start at S. And it says, you better finish at T. And I want the property that if initially, I think initially you're going right. Yeah, no, it looks like initially you're going up. All right, it matters. You can do stuff, and then at the end you should still be facing up. So you have to visit all these faces, but sort of not turn in total. And normally that would be hard to do. If you just tried to visit one face at a time, you can't do that. But if you visit faces multiple times and kind of weave around in a clever way, you can do it. So maybe I'll point with this thing. Yeah. So I start at S, I go up, I turn right. Now I better turn left. I go down over here, up there, I turn left. Then I turn right. So if you follow along here, I just turn right here. So now I go down here, and that is a left turn because it's on the bottom. A little hard to think about. So I turn left here, and then I go turn right, and then I go down, turn left, and then right. It's confusing when I'm upside down. And I come to T, and lo and behold, I'm facing up again. And in fact, I basically just zigzagged. This would also work if it was rotated 90 degrees. I'd initially be going right and then down, and right and down, and right and down. So this can kind of go in a couple of different orientations. And it's really powerful. It also works if T is on the other side of S. You do sort of the mirror image traversal. Now, obviously, I didn't cover the entire surface. I'm leaving room for later. But if this was all I was going to do, I would actually sort of fill out all those strips, just kind of extend them. It just makes this kind of fatter. So this got a little bigger. I've got the first half and then the second half. This is really glued up there. But you can imagine once you have these sort of paths that visit everything, you just fatten them out, and it's no big deal. And also, in this case here, we're imagining, oh, this is actually 2 of them. Fun. 2 of these strips joined together. And so there's a few side faces. They just attach up and down. They're not going to intersect anything, because this is not actually below this. This is way over here. Okay? So that's the leaves. And I still haven't gotten to the exciting part. So imagine you have a band. Just going to represent that by this big rectangle here. And it has a bunch of children. Remember, it could have front children. This is like down in the y-coordinate. And it could have back children up in the y-coordinate. And suppose I'm actually attached to some parent, which is one of my, let's say, is a down neighbor. and I start at some s. Let's say I'm told you have to start here, you have to finish here, and you should preserve orientation because I don't want to have to think about whether it turned. Don't want to have to depend on that. So you can do it. Initially, you must be facing up because immediately I'm going to make 2 right turns. And I could handle 2 right turns as long as the next thing I did was a left. So I come into this thing saying, look, you're facing, this is facing up. Now you're facing down. You better turn left next. And by the end, I still want to be facing down. Okay, now I make 2 left turns. Now I'm facing up again. I tell this guy, you better turn right next and preserve. At the end, you should be facing up again. Now I make 2 right turns. Now I'm facing down, and so on and so on. And here I'm wrapping around to here, because this is actually a band. It cycles around. Then I go in here. It's the same thing. It's just a little hard to see because I'm drawing it on a flat surface. But if it was on a ring, it would be much clearer. Just going left and right, alternating direction, so that I preserve my orientation. At some point, I get to here. I loop around, and I make a little wiggle at some point. And then I can visit all the top neighbors. You just have to slightly switch your orientation. But again, preserve that you're doing left, left, right, right, left, left, right, right, left, left, right, right. Then you will preserve your orientation. You tell each of the children which way you're initially going, and they can deal with it. It's basically telling you whether S and T is like this or the other way around. Okay, so now we end up way up there where the lavender edge is, at T10. Now what? We want to come back here. And I'm not allowed to sort of intersect myself. That would be the paper going into 2 parts of this unfolding. So that's not good. But I have all this space. So natural thing is to just wander from there back down to here using up the space. So it's going to look like this. You visit everything that you did, you just undo. Now where this is painful is not only do I have to undo it in this diagram, but I have to recursively undo everything I did in here, everything I did in here, and everything I did in here. So this recursive thing from this structure ends up getting doubled. At the parent structure, it will also get doubled. At every level of the tree, you're going to double what was below you. So that's why you get exponential in general. If your tree is ugly, like I don't know, something like this, you'll start with something nice and small down here, maybe a constant number of turns. Then you'll double again, then you'll double again, then you'll double again. It'll be exponential. So if this is n, the number of things you're doing here is 2 theta n. On the other hand, if your tree happens to be nice and balanced, doubling is not so bad. Because here you'll have constant. This will double everything below. This will double everything below, but there's only log n levels. And so is that linear? Should be about linear. It's certainly 2 to the theta log n. And it matters what this constant is. I think it's n or maybe n squared, but not too bad. So if you're lucky and the structure of your bands is balanced, this is good. In general, though, it's going to be exponential. Open problem, can you deal with these situations and sort of balance them and only make a polynomial number of cuts? Certainly be nice. Exponential number of cuts is a lot. But it works. You can unfold every orthogonal polyhedron this way. I would love to see an implementation of this algorithm, because you could only do it in a computer, because you'd be splicing into all these little things and it would fall apart. Jason?
You've been making these, gadgets such that voxel would attach just by a side. You could imagine it attaching at a corner, attaching to multiple sides.
So you're worried about, not quite sure. Yeah, what we think about is one band, which looks something like this, attaching to another band. That will always happen on a face. I'm not quite sure what you're imagining. Maybe something like that, where they share a partial face here.
Yeah, but it could also be inset into the.
If it's inset, I'm cutting with every. I maybe didn't mention that. Through every vertex, I'm going to slice with a y-plane. So that will cut into lots of little strips, and then there's no sort of overlap of the strips. I'm subdividing into little substrips. So that sort of deals with that issue. If this was moved that way, then there'll be 3 strips. One over here, one where they're overlapping, and one on the right. Yeah, good question. I forgot to mention the subdivision at the beginning. Speaking of subdivision at the beginning, this leads to another notion which we call grid unfolding. So, the grid of an orthogonal polyhedron is what you get when you subdivide by extending every face into a plane. And cutting with that plane. So that's sort of what I was doing here when they're overlapping. Even in this picture, there's like a face here, this vertical face, and so I'd end up slicing through this thing with a band in sort of that direction. And I don't know, this vertex, you'll end up slicing through this guy. So hopefully you can imagine that. Just slice, with every vertex, slice x, y, and z. That's another way to do it. And that subdivides into sort of a nice grid where every face will now be a rectangle. And rectangles will always meet whole edge to whole edge. So it's a nice simplification. What I'm proposing is add those edges to your polyhedron. It's kind of like assuming that you started with unit cubes and built something, but kept all the edges of all the cubes. I want an edge unfolding of that. Do those exist? These are what we call grid unfoldings. So grid unfolding is an edge unfolding of the grid. This only makes sense for orthogonal polyhedra. Open question, do grid unfoldings always exist? It's essentially the orthogonal analog of this question, edge unfolding of convex polyhedra. If you want to go to orthogonal, just like in between convex and general non-convex, maybe you could hope for grid unfoldings. Edge unfoldings obviously don't work. We had lots of examples where those fail, like the cube with little bites taken out of the edges. But grid unfolding, you get lots of subdivision. It might be easy. Well, it's not easy. I would guess actually it's not possible. The next best thing you could hope for is to refine. So you take each of the grid rectangles and divide it into k by k sort of subgrid. So ideally k is 1 and you're not subdividing at all, but maybe you take every rectangle, divide it in half. Maybe that's enough to then be edge unfoldable. That would be sort of a refined level 2 grid-like unfolding. There are a ton of results about this. They're all partial. Obviously, in the general situation, I mean, this algorithm we just covered, you can achieve a refinement of only 2 to the theta n exponential. When can you do better? In particular, ideally, you get 1 by 1, but maybe you can do something. What? Okay, interesting. One thing you could do with merely 5 by 4 refinement is something called Manhattan Towers. Let me show you a picture of Manhattan Tower. No, that's not a picture of Manhattan Tower. This is more crazy examples of what it's like to visit. This is not this probably is complete, But here there isn't too much doubling because there's only a single child, more or less, everywhere. But the unfolding looks something like that. Here is a Manhattan Tower. So it has a connected base on the xy plane. And then I want to consider z slices as I go up in z coordinate. And I want those z slices to get smaller and smaller, always contained in what I had before. So I never have overhang. That's a Manhattan Tower. And in that case, 5 by 4 refinement is enough to unfold these things. So that's pretty good. Still not perfect, but pretty good. And this is by the same authors like a year before the general result. Let's see. I think maybe I have a movie, yeah. So this algorithm has been implemented at least in some simple examples. And it kind of nicely unrolls. You can see a 5 by 4 refinement in that little staircase. It's again to make everything keep going to the right. But here they find a clever way to visit all the faces without having to revisit basically at all. Just visiting each face a constant number of times. And then we can zoom out. You get the unfolding. So it looks very similar in spirit. Of course, the details is how do you do all that visiting. I'm not going to cover that here. But you get substantially less refinement for that special case. Yeah, another case looks like this. Boom! Isn't that cool? Play it again. This is just slightly more special. So again, I have 3 of them. It's so much fun. It's like exploding a city. Boom! So here, the floor is a rectangle. That's the only additional requirement. And again, it's as you slice upwards, things only get smaller. Here's a bigger one. Boom! So exciting. I could do this all day. So I'm not going to describe how this works, but you could almost reconstruct it from these diagrams. This is what we call an orthogonal terrain. That's the result by Joe O'Rourke. Here, you don't need any refinement. Grid unfolding, 1 by 1. That's pretty sweet. All right, next one is what we call orthostacks. These are like a stack of a bunch of orthogonal polygons, a bunch of bands, basically. This is where the idea of bands came from. This is from an old paper in 1998, from the beginning. So it's just, I have a band, and then I stack another band on top. So each Z cross-section is connected. So that's a little different. And with towers, I could have multiple towers. Here, I really only want one tower built slab by slab. These things, we don't know how to grid unfold. That's an open problem. But if you refine just in Z by a factor of 2, that's enough to unfold. So 1 by 2 refinement is enough for orthostacks. Now, you could go a little crazier and allow vertex unfolding of orthostacks with some grid refinement. And in that case, you don't need any refinement. So grid vertex unfolding orthostacks was the title of a paper. These guys, John Iacona and Stefan Langerman. And it looks something like this. You use the vertex unfolding to fix the direction. Here you're going up, but you really wanted to go right. So it makes things easier. And in fact, the other guys, Demaine, Flatland, and O'Rourke, it's got to be awesome doing geometry and your last name is Flatland. And though she does a lot of three-dimensional stuff, irony. You can do vertex grid unfolding of any orthogonal polyhedron, is what I have written here. I haven't actually read that. I should read that paper. What else do I have? Orthotubes. Orthotubes, this is again in the old paper. Orthotube is just sort of thickness 1 orthogonal tube. It could even be closed, I think, in a loop. But here I've shown it open. And here grid unfolding is enough. You just do all the grid refinement. You can even just do it locally. Technically, there's a slice here that might slice over here, but you don't have to worry about that. You just subdivide into a bunch of boxes, and this can be unfolded in a sort of zigzag fashion. So one by one. You can generalize this to trees also, though it's not totally known. As long as you have a tree of cubes with fairly long connectors in between the branch points, these are called well-separated ortho trees, that works grid unfolding. If you don't have that condition, so you just have cubes connected in some tree-like fashion, it's open whether you can do a grid unfolding. We worked on that in the past. My conjecture is in general, you need omega n refinement. I think, well, my belief is that this kind of exponential blow-up is necessary, but that you can do it only in a balanced tree. And so this would give like linear refinement. I think that's necessary, but we can't even prove that you need 2-by-1 refinement in any example. We don't have anything where grid unfolding is definitely impossible. It's quite a sad state, I guess. It's very hard to prove that there aren't unfoldings, except by exhaustive enumeration. And that's hard to do, because it's slow. We've come up with lots of candidate examples, but eventually we unfold them all. So. All right, I have a bunch of other open problems. This was genus 0. Interesting question is, can you do genus higher than 0, orthogonal polyhedra? I would guess so, but I'm not sure. I think the biggest question is, can you make this non-orthogonal? But then the bands get messy. Haven't been able to do that. All right, I think those are the main problems. Any questions? I'm going to take a break from unfolding now and switch to the other direction of folding. So with folding, we're imagining we're given some polygon, and we'd like to make a polyhedron out of it. It's exactly the reverse of what we've been thinking about. When is this possible? Now, the rules of the game here are different from origami. With origami, we showed from any shape you can make anything if you scale it down. But here, I really want exact coverage. Every point here, or let's say every little patch here, should be covered by exactly one layer over here. Not allowed multiple layers. So this means not everything is possible. I also care about scale factor. But this one, of course, you can crease like this. And more importantly, you glue these edges together. You glue these edges together. These are the opposite of cutting is gluing. We'll be more formal about defining gluing, I think, next lecture. This is just a sort of prelude. But you end up gluing. I want to make something, let's say, in fact, we're always going to talk about folding convex polyhedra. There's very little work on the non-convex case. Though there was actually a recent result. I'll mention that next lecture. If you want to make something convex and therefore sphere-like, you have to get rid of all the boundary. So you've got to glue every edge. You don't have to glue whole edges to whole edges. Maybe you just glue part of an edge to another part of an edge. But somehow, boundary has to get glued up. And if you want something sphere-like, in fact, those gluings have to be non-crossing. I have to be able to draw a picture like this. Question is, when do these gluings make a polyhedron? That is the question we will be answering next class. But first question is, suppose I gave you one of these pictures. I give you a polygon, and I give you a gluing. What this tells you is sort of how to locally walk around. So if I'm here, I could walk over here, go walk over here, go teleport over there, walk over here, teleport over here, whatever. Okay, the gluing tells you locally what this surface looks like, even though you don't know what it looks like yet in 3D. In particular, you can compute shortest paths here. I could compute like the shortest path from this point to this point you might think is, a straight line. But no, it's not. I don't think, or maybe it is. Let's see. A little tricky.
It should be the diagonal of the bottom square.
Diagonal of the bottom square, because these guys are both in the bottom. Very good. So this point is the same as this point. Or no, this point. These get zipped together. This point is the same as this point. So in fact, that diagonal is the shortest path between those 2 points. So you have to think about it for a while, but it turns out in polynomial time you can do that. That's cool. What I want to show now is that suppose you could make a convex polyhedron in this way. I claim you can only make one, never more than one from the same gluing. So I've defined locally what this thing is. It's like a piece of paper, or I could mangle it around. If I want to make something convex, there's only one thing it could possibly make. Finding out what that one thing is quite a challenge. But at least we can prove that it's unique. Sorry about the screeching. And this is Cauchy's rigidity theorem. I think we mentioned it in a previous lecture when we were talking about rigidity and 3 dimensions and like why domes stand up. But now we're going to use it. We're actually going to prove this theorem, and we're going to use it to study these kinds of gluings and say there's at most one way to do this. So a lot of ways to state this theorem, but one way is say, suppose you have 2 convex polyhedra, and suppose they came from the same sort of intrinsic geometry. So there's the geometry of the faces, and there's how they're connected together. So here initially I drew a tree of how the faces were connected together, and then I drew some other connections, like this. So the dual here is, of course, an octahedron. But if you have 2 convex polyhedra, and they are combinatorially equivalent, they have the same way that things are connected together, same graph. And they have congruent faces, so the geometries match also. Then they are actually the same thing. The same polyhedron.
Does that mean that
Up to rotation and translation.
the same set of congruent faces?
Oh yeah, so when I say congruent faces, I mean according to this equivalence. If you take a face on one that has a corresponding face on the other, those 2 faces should be congruent, not just any pair. And they're not all the same. Different faces can be different, but they're identical in pairs. So I'm just saying if you have this picture, basically if you have this picture, there's only one realization. So this picture defines what are the geometry of the faces, how are they connected together. And so if you had 2 convex polyhedra with that same underlying diagram, they have to be the same polyhedron. That's what we're claiming. That's what we're going to prove. Yeesh. This one any better? Yeah, it's better. This is an old theorem. You may have heard of Cauchy, famous French mathematician. Cauchy-Schwarz inequality, all those good things. You don't need to know those. He proved a lot of things. This theorem he didn't actually prove. He wrote a paper about it, or I think partly a letter, partly a paper in 1813. Proof was wrong, and it was fixed in 1934, over 100 years later, by Steinitz. So sometimes it's called Cauchy-Steinitz rigidity theorem, although usually Cauchy. There's a lemma in here that is often attributed to both of them. So, sort of a proof by contradiction. We want to prove uniqueness. So we're supposing, well, maybe there's 2 polyhedra, P and P prime. And they are combinatorially equivalent and have matching faces congruent. What I want to do is look at corresponding vertices. Let's say a vertex V in P and a vertex V prime in P prime. So they're corresponding in the combinatorial equivalence. And then I want to slice the polyhedra, P and P prime, with an epsilon sphere, epsilon radius sphere, centered at V and V prime. Quick mention, if this is not true, if you allow non-convex realizations. You may have seen that example before. These have exactly the same combinatorial structure, same geometry on each face, but one's non-convex and they're different. As long as they're convex, they're going to be the same. In a convex situation, here's what the slice looks like. So here's a little vertex, degree like 5, and I slice the polyhedron with this tiny sphere centered at V. What I get, not the interior, just the boundary of the sphere, what I get are these arcs. They'll be great circular arcs. Can I see? Yeah, here we can see all 5 of them. They're great circular arcs. They're on the sphere. I get a polygon. I get a convex polygon on the sphere. Convex spherical polygons. Convex because the polyhedra are convex. I actually get 2 of them, right? One for P, one for P prime. Polygons. What do I know about those polygons? I know their edge lengths, because the length of an edge here is equal to, if this is a unit sphere, if I rescale the epsilon to be 1, that edge length is actually this angle. That angle is an angle of the face at the vertex. So I know all the angles. I know all the geometries of the faces. I know they're congruent. So I know what these edge lengths are in the sphere. What I don't know are these angles of the polygon. I know the lengths of the polygon, but I don't know the angles of the polygon, because that's essentially the dihedral angle of that edge. And the worry is, well, maybe all the edge lengths match. We do this at every vertex, but maybe the dihedral angles are different. Maybe the convex polyhedron could flex. That's why this is about rigidity. Maybe it's flexible, and then maybe there are 2 different states. All the faces are the same, and therefore all those edge lengths are the same, but the angles might differ. If P and P prime are supposed to be different, then there must be 2 angles that differ. So I want to look at those angles. And I want to label vertex of a spherical polygon. So I have n of these spherical polygons. For P, n of them in P prime. Let's look at them in P. I'm going to label it plus if the angle there in P is bigger than the angle in P prime. Remember, I have a correspondence between everything in P and everything in P prime. Minus if the angle is less, and 0 if the angles are equal. So what I want to show is actually all the angles are equal. Therefore, the polyhedra will be identical. If all the faces are the same, and all the angles at which you join them are the same, and they're connected in the same way, they're the same polyhedron. There's no flexibility there. But it could be there are pluses and minuses. But if there's going to be a problem with this theorem, there have to be pluses and minuses. That's the proof by contradiction. So let's look at one of them. Let's look at a vertex that has some pluses or minuses. So it's a spherical polygon. I'm going to draw it more like a polygon. Maybe there's some pluses, some zeros, some minuses, whatever. First question is, could it be all pluses and zeros? Is that possible? No. Doesn't look good. What does that mean? That it would mean this is like a linkage, right? We're used to linkages. It just happens to be on a sphere. Forget that it's on a sphere. Think of it as almost flat. What that would mean is there's some other way to draw this thing. Basically, there's a way to flex this linkage so that all of these angles increase and this one stays the same. How could I get a polygon where all the angles increase and still be convex? ain't possible. Why is it not possible? I think we've used this fact a couple lectures ago. It's not possible by something called the Cauchy arm lemma. This is the part that Cauchy got wrong, so it's also called the Cauchy-Steinitz arm lemma. And here's the thing. If you have a convex chain, but open chain here, there's a missing bar. So suppose that even when you add the bar, it's a convex polygon, but then I take a convex polygon, remove an edge. This is what we call convex chain. And if you open all the angles, it's increasing all the angles in a convex chain, then this distance increases. It's pretty intuitive. I open all these angles, so I put plus. Some of them could stay the same, but then this distance will increase, as long as you stay convex. I should mention that. But in this situation, we know that both the initial position in P and the target position in P prime are both convex. Okay, let's just take that lemma as given. This is the one I don't like. Then I know, in particular, I can't have all pluses, because then if I just pretend one of these edges wasn't here, I know that that distance must increase. But it can't increase. It's supposed to stay the same. The edge lengths are fixed. So if they're all pluses and zeros, or all minuses and zeros, the same is true just viewing P prime as P and P as P prime. It can't be all pluses. It can't be all minuses. So if there's anything in there other than zeros, there has to be at least one plus and at least one minus. In particular, there have to be at least two alternations. Alternation is either going from plus to minus or from minus to plus. So it could be something like, plus, 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 minus, 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 plus, plus, whatever. Okay, maybe that's your polygon, and that's your labeling. Is that possible? So once you have at least one plus and one minus, you have to have these two switches, at least. Could this happen? No. Right. Because, I don't know, you pick some chord. What do I do here? Just subdivide. All right, whatever. Pick some chord like this one. Not sure it matters. Maybe here? Whatever. These angles down here are decreasing. Therefore, this distance decreases. The angles up here are all increasing. Therefore, this distance increases. Can't have both. So this is also not possible. So in fact, you have to have at least 4 alternations. It's always even. And so it has to be at least a bunch of pluses, then a bunch of minuses, then a bunch of pluses, then a bunch of minuses. And so we're counting these transitions from plus to minus. This is a lemma that we used when we were locking trees, I think. We had a convex polygon. I said at least 2 of the angles have to decrease, or at least 2 of them have to increase, one way or the other. It's because there have to be at least 2 groups of pluses, not only at least 2 pluses, and at least 2 minuses. You might think, well, what happens if there's only 3 vertices? Then you can't have these 4 alternations. Well, yeah, you can't have those 4 alternations, because if you have a triangle, even on the sphere, triangles are rigid. So you would know, if I had a degree 3 vertex, that locally that thing is rigid, it can't flex at all. We're only interested in cases where it might flex locally at a vertex, like the pentagon, like a quadrilateral. All right, so what? This was true at every vertex that was not entirely 0. So if we look at, let's write this down. I really just care about the non-zero edges, the ones that are plus or minus. So I'll call this the subgraph of plus and minus edges. The number of alternations is at least 4 times the number of vertices. I'm going to denote the number of vertices by capital V. Okay? It's page 1. We're going to use a trick. It has many names, I suppose. I usually call it double counting in combinatorics, where you have one quantity, namely the number of alternations. We're going to count it in 2 different ways. We'll get 2 different answers, but we know they must end up being the same. And then we'll get a contradiction. So, what's the second way of counting? Well, we counted local to a vertex. The other natural way to count angles is by looking at the faces. They're also faces, sort of the dual perspective. Every face has a bunch of angles. It has some degree, whatever. They're really kind of the same thing. Oh, here was Cauchy's arm lemma. Beautiful. If you look at the alternations as you walk around a vertex versus as you walk around a face, you'll end up counting them the same number. Right here was an alternation from plus to minus. What's interesting here, before we were thinking of labeling the vertices of the spherical polygon, but in fact, whatever this edge does, it does the same thing local to that vertex as the thing local to that vertex. So really the labels are on the edges of the graph. They could be 0, plus, or minus. And if I have an alternation from plus to minus, viewed from the vertex, it's also an alternation as I walk around the face. So instead of counting by walking around all the vertices, which I just did, and I got at least 4 at every vertex, let's do it from the perspective of the faces. Okay, and we're in this weird subgraph of plus and minus edges, so assume there are no zeros. All right, if I have a face of 2k or 2k plus 1 edges, then it will have, what is it, at most 2k alternations. So I already have a lower bound on the number of alternations. I'm going to try and prove an upper bound, sandwich it between, and show that actually the upper bound is smaller than the lower bound, and that's a contradiction. So this is kind of obvious, right? If you have 2k vertices, no more than 2k alternations. The place where we're making a little improvement is for the odd case. We know because the number of alternations has to be even, you can't get up to 2k plus 1 alternations. It has to be even because for every plus to minus, there has to be a matching minus to plus because it's cyclic. So even here, you can only get 2k alternations. That helps us a little bit. Because now we can talk about number of alternations is at most 2 times the number of triangles. F sub 3 is going to be the number of faces of degree 3. Plus 4 times the number of quadrilaterals, plus 4 times the number of pentagons, plus 6 times the number of hexagons, plus, why did I write 7? I wrote 7. I'm being sloppy. Okay, at that point, I don't care. 7 F7, 8 F8, 9 F9. I'm not going to try to be clever from 6 on, but I'm going to be clever at 5 and 3. Why 5 and 3? Because you may remember from way back when you have a planar graph, because polyhedra are planar graphs, they're convex. The average degree is 5, slightly under 6, one of the 4, 3, 2, 1, one of those numbers. Let's see, should be like 3n minus 6 edges, so that should be 3. Yeah, 3. So most of the faces are going to have low degree. That's the point. So 3 and 5 really matter. But out here, it doesn't matter so much. Good. kind of a magical proof. It shouldn't be intuitive where it came from. But it's really beautiful. You'll see. So it all comes together. Fine. What do I do next? Right. I want to relate. I have a vertex count here. I have a face count here. And I know Euler's formula, hopefully. You know it. It's a cool formula. V minus E plus F is 2. This is number of vertices, number of edges, number of faces is 2 for connected planar graphs. There are other versions when you have multiple components or when you have tori, genus, whatever. But for convex polyhedra, this is true. So this conveniently relates vertices to faces, but it involves edges. So somehow I have to bring edges into the mix. All right, well, edges. I want to count the number of edges in terms of the number of faces. I could do it in terms of vertices or faces. Number of edges is half the sum of the degrees of the vertices. Remember, that's handshaking lemma from way back when. It's also half the sum of the degrees of the faces. If I look at every face and I count the number of edges, I will end up counting every edge twice, once from each side. So this is half the number of faces. Well, number of faces I want to write in this form. So this is half not the number of faces. What am I doing? Half the sum of the degrees of the faces. So this is half. What is the degree of degree 3 faces? 3. What is the degree of degree 4 faces? 4. And so on. Exactly. So now things are starting to look similar, and I want to get some cancellation going on. Use my cheat sheet here. All right, I'm going to rewrite this formula as V equals 2 plus E minus F. Hopefully that's the same. I put E over here, put F over there. We get this. Okay, so now I have E minus F. E is this. F, I have F. Am I missing something here? I'll write the next line. We'll figure out where it came from. Oh, duh. I just skipped a step. F is the sum of F3 plus F4 plus F5 plus F6, okay? All I did here was decrease by, well, because there's a half out here, I decrease each coefficient by 2. Nothing surprising. Okay. So I took E, I subtracted F, just took away one of each. Now I have this formula. That's V. Now, I also know that 4V is at most the number of alternations. So I can get a formula for 4V here, right? 4V is going to be 8 plus, this is going to be like 2. So I get 2 F3 plus, oh boy, 1 times 4 times F4 plus, just double these numbers, 6 times F5 plus, what's the next one, 4, 8 times F6, and so on. All right. Yes. Okay, now, these guys look very similar to these guys. Now here it gets bigger. 8, it's going to go 10 instead of 6 and 7. We also have a plus 8. We don't know whether there are any faces of degree 6 or more, so we can't rely on that. But we have plus 8. So somehow 4V, which is at most the number of alternations, that's the reverse of what we said before, 4v is at most this number, and yet it's also equal to this number. It can't be both. This number is at least 8 larger than that number. Could be even more larger, but at least that. Contradiction, done. This works as long as there's at least one face, meaning there's at least one plus or minus, because we're only looking at the subgraph plus and minus edges. And that is Cauchy's rigidity theorem. Let me quickly tell you, in our situation here, we don't actually necessarily know where the creases are. We just know how things are glued together. Even in that situation, you can sort of figure out where the creases must be, because as I said, you can compute shortest paths once you have the gluing. So you compute the shortest paths between all pairs of vertices, something like this picture, except you don't know what it looks like in 3D. You can still compute the shortest paths. You know every edge must be a shortest path. So the edges are some subset of these guys. And so you've got lots of little convex polygons here. We know it must make a convex polyhedron. If it made 2, Cauchy's rigidity theorem would tell you that they're the same. So even once you fix the gluing, you know there's a unique convex realization. And there will be a unique set of edges from those shortest paths that actually realize it. And next class will be all about how to actually find those gluings and know that they actually will fold into some convex shape and how to find that convex shape. But that's it for today.